Do you need a connector?
Oh, no, I just need to my charger. Yes.
I'm just starting a list in the Google Doc of groups to nucleate, so if you think you should be in one of the groups relating to things you've heard about so far, please add your name there or indicate interest. Again, not just things you want to help with, but also if you just want to spectate to make sure they don't derail or something, that's also an option for level.
It's close enough that you can use your finger.
Yeah, that is true.
I think you're of sufficient height.
Okay, so I'm going to give a
red.
Perfect, thanks. So I'm going to give a quick update on where we are with Bayesian implicit solvent modules, which is a project that started a while ago, mostly led by Patrick originally, and Theo and John, and I've sort of been updating it recently. So, quick review, we're dealing with continuum solvent models where instead of having a bunch of individual water molecules that are represented explicitly, we say there's two regions of constant, dielectric constant, and somehow we want to parameterize what the shape of that interface is. Why? Because it's fast. Both it's faster to evaluate the forces and empirically ends up having faster conformational search. And it also makes it easier to do some reweighting and other things. So implicit solvent is nice, however, it's difficult to match the accuracy of explicit solvent, and it doesn't represent a bunch of things that we know about. It also depends on many free parameters that are fit empirically. The basic structure of the models that we're looking at give each particle charge and some notion of size, and then somehow get out an idea for the shape of the solute-solvent interface. And these parameters, there are a whole menu of different ways to do that, and they're typically fit to solvation free energies, solvation potentials of mean force, PBSA, which is another fluid solvent model. And then after you have these parameters in hand, you might evaluate them by comparing to known structures or other predictions that you might want to make, such as binding affinities. So we're interested in inferring these parameters given one source of solvation-free energies, which is free solve, and doing this in a Bayesian way. So just to make it easy, we focus on the radius and scale parameters of GBSA of BC2, named after its authors. Charges are also parameters in these models, but we'll just use fixed charges from BCC. The structure of the model looks like this. We have a parameter vector theta, goes in this black box, which is simulator or reweighting or whatever. We get out a whole bunch of independent delta G solvation for each molecule in free solve, a star because I'm looking at subsets, sometimes dramatically smaller subsets of free solve. And then we get a likelihood model that is just product of Gaussian likelihood terms. So we say we put a Gaussian centered at the experimental value with a width given by the experimental uncertainty, and we see how far away that is, and we multiply over all the independent predictions. And then here I'm also, for simplicity, using flat prior in all of the parameters. It would be nicer to use something like a real flat prior, such as Jeffrey's prior or something, but for convenience, I'm just using them uniform, but excluding negative parameters. In practice, the way that I do this is, because it's all in implicit solvent, it's very easy to reweight very, very accurately. So I collect a bunch of samples in vacuum, I collect a bunch of samples in some implicit solvent model with fixed parameters, and then I just use mbar to reweight to any new parameters. And this gives me solvation free energies that are pretty, have very low predictive uncertainty.
Even if you change the parameters a lot, you never need to reevaluate.
Yeah, even if I change the parameters a lot, and I don't need to collect a whole bunch of samples to get pretty solid predictions. So this is an ideal test case for working out some of the parameter sampling, the continuous parameter sampling problems that will come up throughout a lot of our other force field efforts, because we can compute these expectations much more cheaply than we can compute a lot of other expectations. So initial results.
Configurations are you using?
Sorry.
What configurations are you using?
So I sample NVT ensemble.
With GAP?
I think.
We're using Smirnoff now, or GAF?
So here was Amber.
It was GAF.
Okay, sorry. I've done several iterations of this. So
Okay.
I guess in the first thing I'm going to show you, this is GAF. Later it's Amber.
Okay. I guess I just, as I'm thinking about it, I'm trying to think it's pretty nicely independent of other parameters, but I guess that there's a dependence there.
Oh, sure, certainly, yeah. The configurations you sample in essentially vacuum or implicit solvent are going to be driven by those torsions, right? So,
right. Okay.
but I think when you say amber, the reason by amber you mean GAF, because GAF is the small molecule version of the for things that are in free solve.
Right.
But Smirnoff is the other one we were thinking it would be useful to derive parameters for Smirnoff.
Right. I use a little bit of some of the definitions that are in Smirnoff for something that I'll show later in the presentation, but
Okay.
I haven't yet done a full,
Okay.
fully using all of
The Smirnoff
the
99
rest of the
Frost.
parameters in Smirnoff 99 Frost for bonds, angles, torsions, and so on. I'm
Okay.
just taking the non-bonded chunk out of it. So it's a little so this is sort of just don't trust any of the actual numerical results out of
Okay.
here. This is just to get a flavor for what sort of problems we're going to encounter once it's easier to calculate these properties, because this is a test bed where it's easy to calculate the properties. So initial results, this is work done by Patrick, and I helped with analysis. We used adaptive Metropolis Hastings, where the covariance matrix of the proposals is adapted using PyMC, generate about 1,000 samples, look at the log likelihood trace, looks like it's reaching stationarity pretty quickly and generating samples that look like they're pretty independent pretty quickly. Then we're interested in a bunch of questions related to what is the distribution over these 24 parameters given free solve, and what does the posterior predictive distribution look like, which means is there some sort of correlation structure in all of my predictions for free solve? Could I have predicted the solvation free energies for most of free solve without doing 235 independent calculations? Could I have just done 10 and somehow the rest of them are correlated with those 10? And then we also want to test how well Gaussian processes would do as surrogates. And Gaussian processes do pretty well as surrogates for mapping from this 24-dimensional parameter vector into each of these delta G predictions using MBAR. However, we're not exactly sure why this is the case. Maybe it's because this is just an insufficiently flexible model, or maybe there's some other sort of bug. But for a lot of the molecules that I generate these plots for, okay, let me tell you what you're looking at. This dotted line is the experimental value, in this case minus 4.8, and all these dots are predictions at each one of these parameters that we sampled. And if you generate an interval of all the predictions that we generated, the actual experimental delta G is outside of that interval. So there's some molecules where it falls in that interval, but for most of the molecules, it looked like it was outside of that interval, and that's sort of a red flag. We're not exactly sure what's going on there. It could just be that the model is inflexible and we're doing things right, or maybe we're doing something wrong.
So the models are very bad.
The models are very inflexible.
We can try other models. There's several implemented in OpenMM, or there's even a custom GB force where you can try to metaprogram models by creating your own pieces of algebraic expressions.
That would be further goal.
But I guess the big question is it really, you said most of the molecules have experimental hydration free energies that fall outside of the range that any parameter set can produce.
Any of the parameter sets that we sampled,
yeah.
which are sample proportional to this.
Yeah.
Maybe, I'm not exactly sure what's going on. It could be maybe there are some small experimental uncertainties and we're biased towards getting those molecules right at the expense of getting all the others
Interesting.
wrong.
Yeah.
Or maybe,
So just to be clear, that's the parameters you sampled if you only fit to one molecule, or that's parameters you sampled when looking at the whole set?
The whole set.
Okay.
Yeah.
Yeah, that doesn't surprise me at all.
Okay.
Like, the models are very bad. I mean, like, we went through and did an experiment where we picked out all the molecules that like disagreed most with explicit solvent calculations, and sort of looked at a little bit about why and varied some sigma and epsilon parameters, and basically found, yeah, those are just terrible no matter what you do.
Okay.
So
maybe they're no bugs. Okay. So.
Like some of them are off by like 8 kcals per mole or something.
Okay.
And if you fix those molecules by adjusting the parameters, it would make everything else terrible.
Okay. So maybe this is also a good test bed for the case that we think we're always in, which is like model misspecification. We know that the correct model, we know that the space of models that we're exploring cannot explain all of the data that we have available. In general, this is true, and this is kind of a limited case where this may be true.
One other concrete example is there's one specific molecule where, with one of these GB models, I think it's this one, no matter what it's a polar molecule where no matter what you do, you get a positive electrostatic solvation for energy.
What?
Yeah.
Okay, that's bad. So I'll.
No one understands why. I've talked to a bunch of the GB people, and they don't understand why. It has something to do with the radius calculation.
But if you do PB, it works
PB
out.
is fine.
Okay, because physically it should.
Yeah,
You can't
exactly.
do that.
So we use this as sort of a test bed to try out and play around with various surrogate models and so on. I'm going to be focusing a lot in the coming months on exploring some other questions with inference over GBSA model parameters. One of the interesting things that I'm interested in, one of the things I'm interested in doing is looking at hierarchical type definitions, for example, using Smarky. If you look at the way that we originally get the atom types, these are just the elements, and then we assign like radius scaling factor and so on that go into the. This is way too small, but I screenshotted a chunk out of the Smirnov 99 Frost definition. So these are all of the 35 non-bonded types, and I just used the sequence of these Smirk's definitions, but truncated them. So I have a hierarchy of models where I start with just one type, 2 parameters, 5 types, 10 parameters, 10 types, or however you should call them. I'm just going to call them types for convenience, but if there's a better term, and so on. And now I have a hierarchy of these GBSA models. And I'm going to sample the posterior with respect to the continuous value parameters for each one of those models, and then do some sort of model comparison experiment. So some details of what I'm going to show you. I'm using
Which GBSA model is this?
OBC2. So the MCMT algorithm that I'm using is the affine invariant ensemble sampler due to Goodman and Weir. The main pro is that it has some pros and cons. The main thing is that it's affine invariant, which means that if you globally scale the coordinates in any direction by any amount, it's all as easy as any other transformation. So that solves the issue of, for example, having to tune the covariance matrix of your proposals or something. Any stretched out Gaussian is just as easy as an isotropic Gaussian. So there are a couple of parameters, but you don't have to tune a whole covariance matrix, which is nice. It's insensitive to global conditioning, and you can generate the proposals in parallel. However, being affine invariant is not necessarily the only thing that matters in high dimensions, and this will devolve again into a random walk in sufficient high dimensions. So it's not a cure-all, but for this sort of problem, it might be helpful. And just to give a flavor of what the proposals are for this sampler, it'll pick subsets. For example, it'll pick 2. So it'll maintain several points within the parameter space. This is the ensemble of gray points. It'll pick 2 at random, and then generate a proposal somewhere on that line. Or it'll pick 3, and then pick a proposal somewhere in an area that's spanned by those 3.
It's the simplex method, but stochastic.
Yeah, it's very similar to the Nelder-Mead simplex method, or but it's an MCMC algorithm. So this is kind of clever, and it seems to work pretty well without any tuning for some problems. And then for convenience, because I need to take a ton of iterations, I'm looking at a very small subset of free solve, just 10 molecules, just 10 randomly chosen molecules. But I'll want to do the whole free solve. then I get these posteriors over the two parameters, the radius and scale factor. In this case, for that one type that describes everything, you see that there's some like weird multimodality and a big weird scaling thing. If I look at the posterior predictive distribution, then sorry, this is way too small, but here I have each of these rows and columns is one of the 10 molecules that I'm predicting on, and the average is taken with respect to the posterior, and we see that there's like very, very strong linear correlations between all of my predictions. I can generate these posteriors for a sequence of increasingly complex models here with 5 Smirky types 10 parameters. See, it's multimodal with these weird scalings and everything. 20 parameters, and now I'm getting, again, close to the limit of how many corner plots I can generate.
Is this discarding some to equilibration?
Yeah, so discarding 1,000 initial samples for the thing. Yeah, so yeah, that was the first thing I thought when I saw this. Maybe it's starting out over here and then it ends up over here, but that seems to be.
And 1,000 is a number that's justified by data, or just a random number?
Just a random number.
Okay.
So each of those itty bitty plots there, what are the axes and what does the plot mean?
Okay, so each of these plots is
The radius and the
it's-
scale factor.
so I have a radius and a scale factor. These two parameters for each of the types.
So this is just showing what's getting sampled.
Exactly.
I
Yeah.
see.
So I have like a 2D histogram and 1D histogram that's just marginal for this is the radius and scale.
Okay.
And then if I have more than 2 parameters, then I generate the combinations. I'm not sure what to make of it, except it's a weird shape. It's not a Gaussian, whatever. So MCMC is going to help you.
I think you should probably use some data-driven method for discarding equilibrium, though.
That is true, and that's easy to do. I think we also run into the issue, even when we get up to 70 parameters, that it seems to be devolving into a random walk. So we have a bunch of next steps and open problems that I'm going to work on, and that I hope to work on with you over the next few months. So one is one of the interesting things that I want to work on is evaluating generalization. So if we fit, for example, JV state models to one subset of free solve, how well can we predict the rest of free solve, or can we do these predictions? How well does fitting free solve transfer into doing host guest binding affinities well? That would be we could set up a bunch of experiments like this. If we start to include other things besides the experimental solvation for energies, for example, looking at the explicit solvent potential of mean force, the solvent potential of mean force, we could use that to further constrain our implicit solvent models. We would like to be able to do some sort of model comparison, so we want to evaluate the marginal likelihoods, such as what Michael presented that Rich had done in 2 dimensions. For more than 2 dimensions, you have to use different methods, for example, AIS or reversible jump Monte Carlo, and those are hard. So I'm looking into that. Biggest thing is using this as a test bed for how to be lazy. So how do I avoid computing all free solve predictions, or more generally, how do I avoid generating all of my predictions for all of the possible observables at each MCMC iteration? Since they seem to be pretty linearly correlated, maybe I could just get away with predicting, a very small subset of them and extrapolating the rest. There are a bunch of practical issues, but this should lend itself to greater parallelization, both for evaluating the likelihood at any given point in theta and over the proposals. And in general, MCMC sampling is difficult. Here I used sort of a black box method that doesn't use gradients, but in dimensions higher than like 10 or 50, we are going to need to use gradients to avoid random walk behavior, so we'll need to look at how to construct something like HMC or electron Monte Carlo for this sort of stochastic setting. And that's all I have. Any other questions?
Or comments on needing to have further discussion as a group on some of this? So right now we are at Mike Gilson on water and then Katie on first guest data. then maybe we'll have a copyright